for a lot of coding interviews, learning data structures, algorithms, time and space complexity, big O notation is pretty much a must if they're asking coding challenges from like LeetCode or HackerRank. But is it any value to those things after you get a job? Does knowing the time complexity and big O notation, is it useful when you actually get into the workplace? It definitely depends on what you're doing, but the short answer is yes, it does matter. And I'm gonna give a simple example of why it does. So imagine an inefficient, wasteful algorithm that performs some sort of database operation or an API call that uses up some sort of credit. This is considered an expensive operation, and if it's inside of an inefficient algorithm, it can cost the company more money or you more money than it should. So in that case, knowing algorithms, data structures, and how to optimize their complexities can potentially save you or the company a lot of money, time, and resources. Let me show a quick example. So this is a common coding challenge from LeetCode.com called 2sum, and it goes, given an array of integers nums and an integer target, return the indices of the two numbers such that they add up to the target. You may assume that it has one solution and blah blah blah. You can't use the same element twice. And then you see here, like, they give an example of an array of nums with 2 and 7 and 11 and 15. The target is 9, and because at index 0 and 1, 2 and 7 equal 9, then your answer you return is 0 and 1. And so I'm not gonna harp on the actual problem so much. I already have the solution, but the key to this problem is there's multiple solutions. And there's an obvious brute force solution, inefficient solution with big O of n squared time complexity. And then there's a more performance solution at big O of n time complexity. And so by using those as examples, I'm gonna talk about how in a real workplace scenario, using one or the other can affect the bottom line. So this is the solution to 2sum that most people come to. It's the brute force solution, big O of n squared. And how it's done is that you loop through with two loops, one with an iterator I and j. And if I and j aren't the same, then you take the two nums out of I and j that's in the array, and you just see if they add up together to the target. So you're basically checking every combination in nums to see which two add up to the target, and then you just return the indices of those two. It works. You know, you can use this in an interview. They're probably gonna ask you if you can do it better, but it works. But the problem here is that it's inefficient. If you have 5 nums, then for every num, you're looping through again for each one. So it's like 5 times 5 if nums is 5 in length. But once you scale up, what if nums was 1,000,000 in length? So then it'd be 1,000,000 times 1,000,000. And so let's do like a little example here. What if accessing nums I costs money? Like, let's just do this as an example just to kind of play around. So let's write a function called get expensive num. And we're gonna put in I, and we're just simply gonna return nums I. And we also gotta pass in nums. And then we're gonna actually have like a cost here that we're going to increment by 1,000. We're gonna say it costs $1,000 to get this expensive num. And I'm gonna put a cost variable up here and start it out at 0. And so it's gonna cost us $1,000 to get this expensive num. So what I'm gonna do is, instead of having nums here, I'm gonna get the expensive nums. And just gonna pass in I and pass in nums. So every time this runs, it's gonna get an expensive num. It's gonna cost $1,000. So, and also whenever I get to my answer, I wanna return what the cost is to the console so we can see what it is. So the cost is going to be this. I'm gonna console out like that. So let's run this. So this is 2sum brute force solution. Just run it. So this costs $397,000 to run. We got the right answer. So our algorithm still got us the 18 and 19 expected output that we're looking for, but it costs us $397,000 to do it. So can we do this better with a more efficient algorithm? Can we get the same output, expected output, but for less money? And we can by writing a more efficient algorithm. So let's look down at this better two-sum solution that actually uses a map. And let's just pretend the map, it's using space, but it doesn't cost us much to use space, but it's gonna cost us more to call this expensive nums. So let's trade space for time complexity by using a map here. And then we're gonna only loop one time, and we're gonna get nums here. And then we're gonna calculate the complement, and we're gonna start storing the nums into this complement map. So every time we see something we haven't seen before, we're just gonna store the number and what index it's at. And so what we're gonna do is every time we hit a new number, we're going to calculate the complement and see if the complement's map has the complement in it, which means that number adds up to the target that we're looking for, because we're calculating the complement by subtracting num from target. And so once we find that we already have a complement in there, then we can just return the index of that complement and then return the current index that we're on. And you can go do the two-sum problem and figure out how that works yourself. This is not important. The more important thing to know is that this solution is more performant by being big O of n time complexity, but it also is more space because it's big O of n space complexity, because at worst case we're going to have to store every single complement or every single number inside a complement's map at worst case. So it does trade for space, but let's pretend space isn't expensive, but calling for nums is the most expensive thing. And so I'm going to change the name of this so that this one runs instead of this one. So like, don't run this one. And so now let's see how much it actually costs. So how we saw how this one costs is we use this get expensive nums to get the nums1 out, or nums I out, sorry. So we're gonna put that same thing here. And then we also need to print out how much it costs when we get to the end. So right before we return our answer, we're gonna print out how much it costs. So let's run that now. Remember last time, this one cost 400,000 K or 400K, something like that. It was like 390K. Now we're gonna run this one and see how long this one takes, or how much it costs. All right, for case one, so now this one's $20,000, 20K. So that's going from, because this doesn't have double loops, it runs a lot less. We're talking 20K cost versus up here where it was 400K. So it's like a 90% reduction or something. I don't know. You can check my math on that, but it's that's a big difference. And yeah, so somebody's gonna come on here and say, hey, this problem's too simple. It's much more complicated than that. Of course it is more complicated than this. But you gotta think about it in the sense as a tiny example that replicates what can happen in more complex application or cloud architecture or whatever it is you're working on. When you scale this up and you actually are using real resources and you have big complicated code bases, big complicated architectures, these little inefficiencies can add up and cost a company or yourself a lot of resources, time, and energy. So knowing how to optimize your algorithms and the way you architect solutions is very important, not just in the interview, but also on the real job. Yes, sometimes there's a disconnect between the interview and the real job, but it's not that it doesn't matter entirely. Like, knowing time complexity and space complexity is still important even outside of the interview. But let me know what y'all think. Love to hear ideas, love to hear feedback. Appreciate you checking out the video.